Hello, and welcome to the Exponential Smoothing tutorial series. In this tutorial, we'll demonstrate Brown's linear exponential smoothing function in Microsoft Excel. For the sample data, we are using weekly demand volume for a hypothetical item. Brown's linear exponential smoothing is best used with a dataset that exhibits trend over time, but no seasonality. So let's examine the dataset for the trend assumption. Using the Excel chart built-in function, draw a trend through the data. The weekly demand data showing a significant downtrend with an R-squared value of around 10%. This is good, so let's begin. Select the empty cell D9. Then type in the function name, equals LESMTH, open parentheses, in the cell or in the equation toolbar. Once you find the correct function, click on the FX button located on the left side of the equation toolbar. This will invoke the function arguments dialog box for the linear exponential smoothing function. Using the function's argument dialog box, specify the input cell range. Lock the starting cell range by pressing F4. In the order field, specify 1 for the time order in the series, or simply put the first observation in the input series that corresponds to the earliest date. For the smoothing parameter, you can type in a value or reference an existing cell. In this example, let's reference the cell value in D1, and then lock the cell reference by pressing F4. For enabling and disabling the function's built-in optimizer, you may use a true-false value or reference a cell in your worksheet. Let's reference cell D2. Lock the cell reference by pressing F4. For the forecast time, we will be forecasting the value at the end of the input data. So set T to 0, or better yet, reference a cell in column A so we can change it after the end of the input data. Lock the cell for column movement by hitting F4 until the $ is showing at the left. For return type, leave blank or type in 0 for forecast. Then click OK. The function returns NA since we don't have enough data, so copy the formula to the cells below it. Copy the formula to cells after the end of the input data. Notice how we change the step value incrementally. The multi-steps forecast of the Brown's linear exponential is a straight line, as is shown in the plot. To quantify the overall forecasting power of the linear exponential smoothing, we will use 3 functions: mean squared error, mean absolute percentage error, and mean absolute scaled error, as shown in cell D4 to D6. Let's try to change the smoothing parameter to 7.5. That's not good. Now the forecast performance measure looks worse. How about 10%? No, that's not better either. In the next part of this tutorial, we will use the function's built-in optimizer to find the best value of the smoothing parameter, alpha. We will also examine the improvement in the forecasting power of the model. That's all for now. Thank you for watching.